Okay, today I want to share something that I think is pretty cool. This is Herbert Gross's latest book, Lens Design for Imaging, Volume 1. There are actually other volumes, and in fact, he's told me that he's much happier with the other volumes, or much more proud of the other volumes. But this one is also pretty good, right? This book came out, I think, sometime last year or this year. I can't remember which year it was, but fairly recently. Okay, so what I want to highlight is that if you turn to page 259, there's a section called effective aperture. So I'm going to tell you guys what that is in a minute. But before I do that, there's a reference to a paper of mine in 2005. Why that is because the effective aperture originated from this paper. All right, and this is something I presented at a conference in San Diego in 2005. And right around the same time, I had a discussion offline with Ken Moore, who agreed that it was a useful formulation. So it is actually cited also in the Zmax manual. You'll see effective F number. There's actually a merit function operand for that. This equation is written in a form that he prefers, that Ken Moore prefers, but the mathematical formulary comes from this paper. To be fair, before this came along, Matthew Rimmer had um, expressed and mentioned that his original paper on relative illumination can also be used to formulate an effective aperture or an effective F number. He doesn't really go for the formulary, but he does mention that. So that's to be fair to him. I only found that out right after I wrote this paper. But when I was writing this paper, I independently came up with the entire formulation and mathematics and everything. So anyway, so that's pretty cool. So what is this? What is the effective F number? So if you look at the exit pupil for any optical imaging system, and if you assume that the aperture stop can have any arbitrary shape, not just circular, not just rectangular or square, but any kind of arbitrary shape, right? Like this weird shape right here. And if you take all the axial rays that surround that aperture, each ray has a certain angle to the optic axis, right? Okay, so the irradiance, the axial, that means the on-axis irradiance, is given by pi times the radiance, assuming it's a Lambert source, times numerical aperture squared. That one we know from having a circular aperture, circular pupil. But what happens if you have a non-circular aperture, some arbitrary shape aperture? Well, you can also associate that aperture with a kind of effective numerical aperture. And the way you do it is to mathematically arrive at an integral of cosine fourth of this theta, and integrate that around the entire aperture, around the entire exit pupil area. Okay, if you did that and if you equate both sides of the formula, um, and solve for numerical aperture, you get this. So this is your effective numerical aperture. And if you want to define an F number, then the effective F number is 1 over twice of that effective aperture. Now, that's not all. Okay, this is very cumbersome algebra. If you want to make it numerically integrable, divide this into pi slices, pi's around the area, and sample around there. And when you do that, you end up with a summation. And what it tells you mathematically is that the effective F number, backtrack, that the effective numerical aperture is approximately equal to the root mean square of the average over of numerical apertures around sample around the aperture. Does that kind of make sense? Anyway, this is talked about in that paper of mine. If you backtrack, you can look at that. And it's also discussed and derived in my book called Perspectives on Modern Optics and Imaging, published in 2017. It's also republished by SPIE in 2024, so you can find it there as well. And where else can you find it? You can find it. That's it. That's it. So that's what it is. Okay. That's what I want to share. Anyway, thanks.